We've been talking about renal physiology, subject to chapter 25 in our Marieb book. We've talked about glomerular filtration and its regulation. We've talked about reabsorption of fluid in the proximal tubule, where 2/3 of the fluid and solutes and all the organic nutrients are reabsorbed. And we've talked about reabsorption in the loop of Henle, and finally in the distal tubule. Now we'll just take a brief moment and emphasize some things about tubular secretion, adding stuff from the blood into the filtrate at any point beyond the glomerular filtration step. And then we'll talk about how the kidneys can concentrate urine, more concentrated than plasma to conserve water, or dilute the urine more dilute than plasma in order to get rid of excess water. Finally, we'll talk about some clinical applications, how we can use our knowledge about how the nephron works to cause the kidneys to get rid of excess water so we can control blood volume and blood pressure for reasons of clinical necessity. All right, so let's look at tubular secretion a little bit. Tubular secretion, we're going to transport potassium into the tubule. As you already know, that's going to be under the control of aldosterone in the distal tubule. We're also going to get rid of hydrogen ions and ammonia occasionally by adding it into the tubule, transporting creatinine into the tubule. I'll just make brief mention. Hydrogen ions are produced every day during cellular metabolism. There's always a net production of some acid by cellular metabolism, by digestion also of certain components of your diet. And so we need to get rid of those hydrogen ions. They can't accumulate in the body or you'd become more and more acidic until you'd wither in a little black smoking ash. Before that happens, we're going to secrete those hydrogen ions into the urine and get rid of them. We'll see in chapter 26 exactly how that can be done without acidifying the urine unduly and causing some discomfort, which wouldn't be very pleasant. And in that process, we'll also see that ammonia may be produced under certain conditions and secreted into the tubule. Creatinine is an amine, a nitrogen-containing compound that's produced as a result of creatine metabolism. You know about creatine and creatine phosphate from muscle physiology. Well, the creatine metabolism produces a waste product, a certain amount of creatinine every day, and it's always in your blood, and then it's filtered in the glomerulus, but then any additional creatine in the blood flowing through the kidney is going to be secreted into the filtrate. So there will be essentially no creatinine, leaving the kidneys in the blood as it exits. So the functions of why do we do tubular secretion? Again, we got to get rid of some amine-containing waste products. You'll notice as we study more about the clinical aspects of analyzing kidney function that there's a variable called blood urea nitrogen. How many amine-containing substances are there in the blood at any given moment? And the kidney's job is to maintain that level and get rid of creatinine, get rid of ammonia, get rid of urea. Those are the amine-containing substances, and if the kidneys aren't doing their thing, blood urea nitrogen starts to rise. But the kidney's job is to secrete those amine-containing substances, those waste products. We also are going to get rid of any drugs that are bound to plasma proteins. If there's a substance that's hydrophobic and bound to a plasma protein, for example, or a carrier, it won't be filtered in the glomerulus because the plasma proteins are retained in the blood during the filtration step, and so we're going to instead take those substances, strip them off, and secrete them into the filtrate in order to eliminate them in the urine. We know that secretion is important in getting rid of any dietary potassium. Blood potassium levels have to stay constant, and so there's a secretion step mediated by aldosterone in the distal tubule. And finally, as I said, there's some acid produced that needs to be gotten rid of every day in the tubule. Okay, how does the kidney concentrate urine or produce dilute urine to accommodate the needs of the body with respect to blood volume and blood pressure? The first thing in the process of being able to concentrate urine is to produce this salty interstitial medulla. We already talked about that a little bit, so I'll just review that again with you in a second. We're going to have a way of letting some salt accumulate in the interstitial fluid of the medulla of the kidney. And then we're going to vary the permeability of the collecting ducts as they pass through that salty region. I've been using the term osmolarity a lot to refer to the overall concentration of solutes in body fluids, in the blood plasma, for example, in the filtrate. And more formally, osmolarity is the number of moles of a solute, or of all the solutes, I should say, together per unit volume, per liter of solution. That's osmolarity. If you sum up the molar concentrations of all the solutes in a solution, that's the osmolarity. Osmolality is a popular alternative term to describe concentration. A lot of people like to talk about osmolality. Chemists like to talk about osmolality. The only difference is we're talking about solutes, the number of solute particles per kilogram of solute, or of solution, I should say solvent, instead of per liter. Kilograms instead of liters. Very similar. So if you see the term osmolality, you can just substitute in your mind osmolarity. It's a concentration term. All right, so how do we express it? Milliosmoles, usually, when we're talking about physiological concentrations, per kilogram would be milliosmolar osmolal solution, or the symbols small m for milli, os for osmo, and then the capital M refers to the per kilogram value. So if you see a capital M, it could be osmolality or osmolarity. It's just a way of designating the concentration. Anyway, it reflects the osmotic pressure of a solution. How much can the solute in a solution draw water onto itself by osmosis? That's why it has the term osmo. If you sum up all the solutes concentrations, that determines how avidly they will attract water by virtue of those particles that are present compared to another solution of a different osmolarity or osmolality. So what is the osmolality of body fluids? Well, we've mentioned before, but I'm reiterating for you now because it's really important in this context. Body fluids, including blood plasma, are 300 milliosmoles per liter, or milliosmoles per kilogram of water. So that's the normal osmolality of your body fluids, 300 milliosmoles per kilogram or per liter. It's the kidneys that make that so. They control the concentration of solutes in your plasma at that 300 milliosmolar level. We know one way they do that. We talked about aldosterone in the last section. We said that aldosterone fine-tunes the reabsorption of salt and water in the distal tubule, and that has an impact on osmolarity, because if we add a hypertonic solution by action of aldosterone, we'll raise the osmolarity and volume of the blood. Now we're going to talk about the role of ADH in controlling urine composition, and namely how we can concentrate urine. ADH allows us to concentrate urine. There's some terminology associated with this process. We've already talked about every important step in this process, but there's some terminology that I'll introduce. The countercurrent multiplier is the term used to describe all the processes taking place in the loop of Henle that result in accumulation of salt in the medullary interstitium. So we'll just take another quick look at that again. The countercurrent exchanger we haven't talked about. It's the capillaries, the blood capillaries of the juxtamedullary nephrons. We looked at them in the very beginning, and now we'll take a closer look at them and see how it is that they help us out with this process of concentrating urine. So, countercurrent multiplier. It's just a term to describe the process by which the fluid flowing down in the loop of Henle back up in the ascending limb, and the pumps in the thick ascending limb can produce this salty interstitium. There's some description of how that works. Really, I think we've already covered pretty much what you need to know about how that's happening. Here's a picture of the loop of Henle, and we saw that in the descending limb, water is absorbed by osmosis. And then in the ascending limb, salt is reabsorbed by diffusion, but in the thick ascending limb, a lot of salt is reabsorbed by active transport, primary active transport. And with the sum of all those properties of the loop of Henle result in accumulation of salt. That is called the countercurrent multiplier. That's where all the salt in the medullary interstitium comes from. And here's just a little flow chart. If you didn't understand that, I think you're having no problem at this point understanding that. In the ascending limb, the thick ascending limb, salt is pumped out into the interstitial fluid. That causes the interstitial fluid to increase in molality or concentration. Therefore, water leaves the descending limb by osmosis since it's water permeable. The fluid, the filtrate begins to rise in concentration. We already saw a little diagram of that last time. And then as the fluid begins to rise up, back up towards the cortex, the fluid is now more concentrated than the surrounding fluid, the surrounding interstitial fluid, and salt is reabsorbed by a diffusion. And then finally, back to the beginning, salt is being pumped actively out of the thick ascending limb of the loop of Henle. So that's the process of creating the salt environment, the countercurrent multiplier. The countercurrent exchanger is really just a feeding station or mechanism for all the cells in the medulla, all the cells of the loop of Henle, all those epithelial cells, all the cells of the collecting ducts. Those cells need nutrition. They need blood supply. And the countercurrent exchanger is nothing more than a way of providing a blood supply for all those cells in the medulla without stripping away the salt that we've so carefully placed there. So the countercurrent exchanger, the vasa recta capillaries, are permeable to salt and water. So as the blood flows down into the medulla, it becomes saltier and saltier. Salt diffuses in, water diffuses out until it reaches that hairpin turn. And then as it starts to ascend in the loop of Henle, salt diffuses back out again and water diffuses in. So it gets concentrated on the way down, it gets diluted again on the way back up, and we haven't changed anything. We haven't taken away any salt that was in the interstitium of the medulla, yet we've brought some nutrition, we've brought oxygen, we've brought a blood supply to all those cells down there. Let me show you what I'm talking about. Here's a little picture of a vasa recta capillary, the peritubular capillary of juxtamedullary nephrons. The blood, as it descends, is faced with a difference in concentration between the plasma and the extracellular fluid, the interstitium, and salt diffuses in, right? We have that salty environment. I drew in there some concentrations. As we move down into the medulla, it gets more and more salty. Salt diffuses into the blood. Water diffuses out by osmosis. Then on the way back towards the cortex, the blood is now more concentrated than the environment it encounters, and water diffuses back in by osmosis and salt diffuses out. And when we reach back to the cortex, the fluid is almost back to 300 milliosmolars per liter. So we really haven't taken away any salt particularly with us, but we've fed all those tissues down there. Incidentally, the countercurrent exchanger also picks up all the water that's reabsorbed by the nephron in this area, by the collecting ducts, by the descending limb of the loop of Henle, and so the volume of blood is actually greater. So the water doesn't accumulate in the interstitium during water reabsorption. It's taken away by these vasa recta capillaries. So the loop of Henle creates the salty interstitium, and the vasa recta feeds the cells in the medulla without stripping away the salt. It preserves that interstitial salt gradient. So now what? We've got a salty interstitium when we fed the tissues. Now what? As the filtrate goes on its last leg of its journey down through the collecting duct, water is reabsorbed by the salty interstitium of the medulla. Water just reabsorbed by osmosis. We can see the concentration of the medulla as we go deeper and deeper down through this collecting duct. The concentration of salt out here reaches as high as 1,200 milliosmolar, and the fluid in the collecting duct, as you may remember, is very, very dilute, maybe as low as 50 milliosmolar. So very dilute fluid coming from the collecting duct or from the distal tubule into the collecting duct, and as it travels down into the salty environment, it becomes more and more concentrated, and it may achieve a very high concentration. That only happens in the presence of ADH, Antidiuretic Hormone. During dehydration, the hypothalamus releases Antidiuretic Hormone, which makes the collecting ducts permeable to water. This is a picture of the collecting ducts in the presence of ADH. They're permeable to water, and we can concentrate the urine, reabsorb the majority of that water. The urine is going to be excreted at 1,200 milliosmoles per liter potentially, or some concentration much greater than that of plasma. That's how we can conserve water, reabsorb that excess water or that needed water, and pee out a very small volume of concentrated urine. However, if you're overhydrated, your osmolarity of your plasma is going down. If you just start drinking water, that water is absorbed in your digestive tract right into the blood. Osmolarity of plasma goes down, blood pressure goes up, and your hypothalamus reduces the ADH secretion, and now the collecting duct becomes impermeable to water. And that dilute filtrate coming from the distal tubule just travels right down through the medulla into the calyces, and we pee out a large volume of dilute urine, maybe as low as 50 or 100 milliosmoles per liter. That clear urine you see when you drink a lot of water, and then you find yourself having to run and dissipate that. Here's a little graphic illustrating that same thing. If you're overhydrated, the hypothalamus reduces ADH secretion, the collecting duct remains impermeable to water, and the dilute filtrate produced by the ascending limb of the loop of Henle and the distal tubule just travels right on down through, and we pee out a large volume of dilute urine. However, if you're dehydrated, blood pressure is going down, plasma osmolarity is going up, right? We're sweating out water, for example. ADH is released, the collecting duct becomes permeable to water, and as that dilute filtrate from the distal tubule travels down into that salty medulla, we reabsorb water by osmosis, and the urine gets more and more concentrated, and we pee out a very small volume of dilute urine. So that's the story with respect to concentrating urine when we need to conserve water, or diluting the urine when we have excess water on board. That's probably it for this section. We'll have another section in which we'll talk about diuretics, how we can control the reabsorption of water in order to get rid of some volume when we want to manage the blood pressure, say, clinically, and we'll see how that works.